just make sure that I record this. Okay, Bismillahirrahmanirrahim. Assalamualaikum. Okay, again. Right, before we move on, I would just like to re-emphasize, okay, especially this is for your previous homework, not the one that I just assigned to you yesterday. This is for the one that I assigned to you on Friday, okay? So for this example, okay, using the same example, you have already worked out the order for X, okay? Looking at experiment 1 and 2, you were able to find the order for X because only X is changing between experiment 1 and 2 whilst Y is constant, okay? So fine, X is first order. And then to find Y, okay, I choose experiment 2 and 3. You can always choose experiment 1 and 3. That's fine. Okay, I choose 2 and 3 because it's easier. So the concentration of Y increases by 2. Okay, I know that you're only focusing on Y, but you must not ignore the fact that X is also increasing here. Okay, X is increasing by 2. So that means your rate is affected by both the change in Y, concentration in Y, and the concentration in X, okay? Now, for this example, it's easy because, I mean, it's more obvious because the rate is increasing by 8. So if you look at just Y, increasing the concentration of Y by 2, the rate increases by 8, it doesn't make sense, okay? So that means there must be other factor that is causing this, okay? Right, so the increase in rate by 8 is actually a combined effect. So this is what I mean by a combined effect. This effect is caused by both the increase in concentration of X and the increase in concentration of Y. So if, I don't remember which question, but if your rate is increasing by 2.5, for example, and then your concentration is increasing by 2, you cannot just assume, oh, increase by 2, increase by 2.5, it's more or less the same, then it is first order. You cannot just assume that, okay? You have to look at the other reactant as well. Is there any changes to the other reactant? Because that 0.5 can be caused by the change in another reactant, okay? The change in concentration of another reactant. So please check again your corrections. I've already uploaded all your work from the Friday assignment onto the OneDrive, okay? All of you should be able to access it. Look at your own paper. If you want to refer to your friend's paper, that's fine as well. I don't have a problem with that. So look at your answers, look at the correction. If you need to correct your answer in the paper, please do so, okay? Don't just leave it, because otherwise later on, if you don't do it now, you will forget about it, and come revision for your exam in November, then you don't know if your answer is correct or not. So please, while you still remember and while you still have time, you're at home, you can't go out, please write down redo the correction or write down any comments that I have written down on your paper on OneDrive, okay? Right, so that's orders of reaction. Now we move on to the rate constant, which is what we've already gone through this as well, right? Yes, this one you have done as well. You've handed in, I've also marked it. Now we want to talk about the rate constant K and its effect on temperature. Have we done this or not? Because if we have, then I'm just gonna go through it quickly. Can anyone let me know if we have done 8.2 together? No, okay, right, thank you. Okay, so rate constant K is only affected by the change in temperature, okay? If you change the concentration, your rate constant will not change. Change concentration, rate will change, but not the rate constant, okay? So there is a difference here, right? Rate will change when you change the concentration, but rate constant will not change. Rate constant is just like your equilibrium constant. They do not change except when you change the temperature, okay? So again, rate constant is not affected by the addition of catalyst, by the increasing concentration, or by increasing the surface area. They will not change except for temperature. Okay, the effect is proportional. If you increase temperature, the rate constant will also increase. Right, so that's all that's all for that particular learning objective. Right, moving on, we want to look at what is the relationship between a rate equation and a mechanism. Okay, right, what is a mechanism? This is an example. Well, you don't have to copy this because later on you will copy this down on page 10. Okay, right, so this is an example of a mechanism. It's something that I hope you are familiar with because you have already come across this in AS. This is the SN1 mechanism of halogenal alkanes. Okay, written on top of this example, this is the equation. Okay, the equation is just like a summary. The equation tells you your starting material and then your final material. It's very simplified, summarized. Okay, mechanisms, however, it shows you the step by step. Okay, it shows you how the bond is breaking. It shows you the movement of the electrons, that these arrows are showing you the movement of electrons, and then it is showing you the formation of intermediate. Okay, this intermediate is also something that you have already known. It's called carbocation, right? But why do you not see intermediate in the overall equation? Okay, this is because the intermediate is being used up in that reaction, right? Another thing about mechanisms is that it tells you how many steps it requires to get from the reactants to the products. Okay, overall equation, this one here, only tells you, well, it looks like it's just a one-step process. You start from a halogen alkane, water, and then you form your product, which is an alcohol, and hydrogen bromide. So that looks like a one-step process, but actually reactions, chemical reactions, are much more complicated than that. They are made up of several steps, or we call several stages. Okay, that's where the mechanism comes in. The mechanism will tell you that for this particular example, SN1 of a halogen alkane, it actually involves two steps or two stages. Okay, first is the breaking the bond of the carbon-bromine bond, and then you form the carbocation, and then you form the anion. Later on, the carbocation is being attacked by the water, and then you form the product. Okay, so what is the relationship between the mechanism and rate equation? Now, these mechanisms that we have learned, actually, back then, the chemists, they did not observe this. Okay, it's not something that you can observe, something that you can look into a microscope, because electrons are very, very small. You cannot see it moving. Okay, the breaking of the bond also, you cannot see it visually. It's a concept, it's an idea that the chemists come up with based on the data, based on the rate equation. Okay, so mechanisms is not, it may or may not be the actual thing that is happening. Okay, it is being how do I say this, the chemists that are the ones who come up with these steps. These are their suggestions. Okay, so this may or may not be necessarily happening in real life, but this is the best explanation that we can use to tell how the reactants transform into the products. Okay, so that's a little background of anything that we call mechanisms. Okay, the definition of mechanism is a series of steps, right? Through which the reaction progresses, often forming intermediate compounds. So in this example, your intermediate compound is this carbocation, okay, the one with the positive charge. And then if you add up all the steps in the mechanisms, you add up all the stages in the mechanisms, this will give you the overall equation for the reaction. Okay, so here you have step 1, step 2, and when you add them up together, you will get the overall equation. Okay, how do you add them up? You just put all your reactants on the left and all your products on the right. And hopefully you can see that since I have a carbocation on the left and a carbocation on the right, they cancel each other out. So that's why you don't see carbocations in the equation. Okay, right. Each step can have a different rate of reaction. Okay, so for example, again, using this example one, this is step one, this is step two. Step one and step two will not have the same rate. Okay, even though we always say, okay, for example, the rate for this reaction is 8 mole per dm cube per second. Okay, I'm just going to use a random number, 8. But actually, when you break it down into the mechanisms, you cannot say for sure that step 1 is 8 mole per dm cube per second, step 2 is 8 mole per dm cube per second. Okay, no, because in a mechanism, there will be one step, one stage where it is the slow process. Okay, the slow process is called the rate determining step. I remember mentioning this to you, and if you go back to your mechanisms in organic chemistry AS, you may have noticed that I wrote RDS on the mechanism. This RDS stands for rate determining step. Okay, so again, if we look at example 1, the first step happens to be the rate determining step. How do you know that? You can't possibly know that unless they tell you the relative speed. If they say this step is the slow step, that means that's the rate determining step. Okay, the fast one is not the rate determining step, right? So if there is another reaction where it has 5 stages, 5 steps to transform the products into the reactants, 1 out of 5 of these steps will be the slower one, and the slow one is the rate determining step. Okay, which one is it? You will not know unless you analyze the data from the reaction. Okay, so actually the rate equation can tell you which one the slow step is. Okay, moving on to the next one. Right, so this is just the mechanism of what I was talking about earlier on. So connecting the slow rate determining step and the rate equation, what's their connection? Why are we suddenly talking about this slow step or this rate determining step? Okay, the particles that collide together in the rate determining step, so that's saying the reactants that are in the slow step are the same substances that appear in the rate equation. Okay, if a substance does not appear in the rate equation, it does not take part in the rate determining step. So what do I mean by this? Rate equation, do not get confused. If I go back to my example, this is my equation, overall equation. Okay, my rate equation is equals to K times the concentration of something raised to the power of something. Okay, now, so what I was saying earlier on, it says that in my rate equation, okay, the reactants that are in the slow rate determining step will appear in the rate equation. Okay, so if I know the mechanism and I know the relative speed, I can say that, don't worry about this example. I have a few examples to show you after this. Now, between these two steps, I know that the first step is the slow rate determining step, RDS. Okay, and I know that the reactance is this. That means my rate is equals to K times by the concentration of this species. That is all. Okay, I'm just going to do this really quickly. CBRN, because I have one molecule, so the order is to the power of 1. H2O, H2O is my other reactant, but H2O does not appear in my rate determining step. It appears in the next step, which is the fast step, which I don't care. Okay, that's why this is what the statement means. Okay, the species that appears in the rate equation is the one that is also involved in the slow rate determining step, right? Okay, So now you have another method of finding the order of a substance or a reactant. Okay, you can actually use the mechanism to determine the order, but less likely you will be given mechanisms like this and then asked to find the order. They want you to use rate and concentration to find order, the ones that we have looked at previously. Okay, but my point is that, right, there are two things in this, there are two reactants in this example, but only one of them shows up in the rate equation because that same species is the one that is involved in the slow rate determining step. Okay, H2O is another reactant, but it doesn't show up in the rate determining step. That's why it doesn't show up in the rate equation as well. Okay, right, moving on. If there is only one species in the rate determining step, it is unimolecular. So going back to this example, I only have one species in my slow rate determining step. So this mechanism is called the unimolecular mechanism. Okay. If there are two species in the rate determining step, which I will show you later on, then we call it bimolecular. Right? This unimolecular and bimolecular is actually the numbers in your SN1 and SN2 mechanism. SN1 mechanism means that it is unimolecular, one species. SN2 means it is bimolecular. You have two species in the rate determining step. Now, this example is a unimolecular SN1 because I only have one species in my slow rate determining step. That is how I memorize my SN1 and SN2. I don't memorize it as SN1 is usually for tertiary, SN2 is usually for primary, okay? I memorize it by looking at the mechanism, right? Slow step, there's only one species, unimolecular, therefore SN1. Okay, now looking at example 5. Right, so I'm just going to use a general reaction first. In this general reaction, I have reactant A reacting with 2 moles of reactant B and 1 mole of reactant C to form product D and plus product E. If I just look at the overall reaction, it looks like it's a one-step process, but that's not true because the mechanisms told me that there are 3 steps, okay? Step 1 is A first reacting with B to form X. Now you notice that X is not appearing in the overall reaction, overall equation. That means your X is an intermediate, okay? Plus product D. Okay, I see my product D in my equation. And this first step happens to be the slow step. So that should already be a hint for you that this is your rate determining step. Okay, and if it's this step that is your rate determining step, your rate equation should only contain A and B. Okay, C does not appear in the rate determining step, so C is not present in your rate equation. Okay, I will talk about this shortly. Moving on to step 2, your intermediate X is now reacted with C. Essentially, it is being used up to form another intermediate Y. Okay, this is a fast reaction, so I don't care about them. Your Y intermediate is again reacted with B, so essentially your Y is being used up, destroyed, and then to form product D. Okay, when you add up 1 plus B plus X plus C plus Y plus B, your B becomes 2B. Okay, you have X and Y on the left side, and then you add up your X plus D plus Y plus E. X and Y on the right side will cancel out with the X and Y on the left side, and you form D plus E. So adding all these 3 steps will give you the overall reaction. Okay, I'm not going to show you here, but if you want to do that on your own notes, that's fine with you. Just cancel out whatever you have on both sides, and in this case, it's X and Y. Rate equation is equals to K times the concentration of A to the power of 1, concentration of B to the power of 1, concentrations of C to the power of 0. Now, C to the power of 0 is essentially just 1, okay? Which is, you don't see it. You don't see it in the rate equation. So this is what I mean. If you look at the slow rate determining step, you only have A and B. That's why in your rate, you also only have A and B. So if they ask you, what about this? What about reactant C? Why is it not in the rate equation when it's actually a reactant? Well, it just means that C is to the power of 0, or we say that C is 0 order. Now, by definition, 0 order means no matter how much you change the concentration of C, your rate will not change. Okay? A, if you change the concentration of A, your rate will change. If you change the concentration of B, your rate will change. By how much? Depending on the order. Since both of them are first order, so the relationship will be directly proportional. Increase A by 2, rate increases by 2. Increases B by 3, rate also increases by 3. Okay, so the rate equation can actually tells you so much about the mechanism. Another thing is the number of moles or the number of molecules in the rate determining step can also tell you the order. Okay, so you have 1 mole of A here, order is 1. You also have 1 mole of B, the order is 1. Okay, C is 0 order as it appears in the mechanism in a fast step, which is after the slow step. Right, next. So X is the intermediate. Y is also another intermediate that I forgot to mention. Okay. This slow step does not involve C directly. So you do not have C in the slow step. X is an intermediate derived from A and B reacting together. Okay. So this is something that I've already explained to you just now. Now, the type of mechanism, is it a unimolecular or a bimolecular? We look at the slow rate determining step. Okay, you have A and B. You have 2 types of species reacting in the rate determining step. So if you have 2, it's bimolecular. All right. I hope that's clear for everyone. Moving on to example 6. Now we use a real example. So we have a reaction of a nitrogen dioxide gas reacting with the carbon monoxide gas to form nitrogen monoxide gas and carbon dioxide gas. Okay, so you have 2 reactants here, nitrogen dioxide, carbon monoxide. Now, and then they tell us that the mechanisms involve 2 steps to convert the reactants into products. And it turns out that step 1 is the slow step. Now, do not assume that do not assume that step 1 is always the slow step. It does not mean that. The slow step can be step 2, step 3, step 4, or even the last step, step 5. Okay, so it's just coincidental that so far our slow step is the first step. Okay, so if we look at step 1, we have nitrogen dioxide reacting with nitrogen dioxide to form nitrogen monoxide and nitrogen trioxide. Now, if you notice, nitrogen trioxide is not shown in the overall reaction, overall equation. That means NO3 is an intermediate, and the intermediate will have to be used up in that reaction. Okay, so as you can see here, the nitrogen trioxide is being used up, being reacted with carbon monoxide to form NO2 and CO2. Okay, now if you add these 2 steps together, NO2 plus NO2, you've got 2 moles of NO2 plus NO3 plus CO on the left side. On the right side, you've got nitrogen NO plus NO3, NO2 plus CO2. Okay, so 2 NO2 on the left side will cancel out NO2, so that becomes 1. Your NO3 will cancel out, which is completely gone. That's why you don't see it in the overall equation. Okay, now given the fact that step 1 is a slow step, that should already give you a hint that this two species, hold on, these 2 species must appear in your rate equation. Okay, so and it does show your rate equation is equals to K constant. Okay, that will always be there. times by the concentration of NO2. Now, since you have 2 moles or 2 molecules of NO2, this tells you the order is 2. Okay, if you only have 1, then the order is 1. So the mechanism and the rate equation work with each other. Okay, they actually give you an insight. Actually, in real life, what the chemists do is that they can only find the rate equation based from experimental data. Okay, first they do experimental data, they find the order of this nitrogen dioxide, then only they work out the mechanism. Okay, that is what they do in real life. But in our case, sometimes we are given mechanisms, we work out rate equation. Or the more difficult one is, given rate equation, then we have to work out the mechanism. And yes, you are expected to do that in the exam. They will always ask you, what is the possible mechanism based on the given rate of reaction. Okay, so that should tell you if NO2 appears in your rate equation, that means NO2 is in the slow step, rate determining step. The fact that it's the second order means that there are 2 molecules of NO2 in the rate determining step. Okay, now this is another example of a bimolecular mechanism, because in the slow rate determining step, you have 2 molecules reacting with each other, even though they are the same molecule, but still considered 2 molecules. Okay, next, example 7, right? Okay, so I need you all to unmute your speaker, because you need to answer me on this question. I have 10 minutes left, right? So let's have a look at this reaction. We have 2 moles of N2O5 to form 4 moles of nitrogen dioxide and oxygen. This equation turns out to take place in 3 steps. There are 3 stages, okay? Which step is the rate determining step? Now, if you just look at the equation, you wouldn't be able to determine which one is the rate determining step, okay? You need the rate equation, right? The rate equation is equals to K times by the concentration of N2O5. Now, between step 1, 2, and 3, which one is the slow step? 1, 2, or 3?
Step 1.
Okay, I'm hearing step 1.
1.
Any other answer?
1.
1. Any
1.
more? Step 1 is the slow step or the rate determining step. Okay, so that's right. Step 1 is the slow step and it is the rate determining step. So that means 2, 3 is fast. Okay, why do you say this? Because in the rate equation, N2O5 is appearing. Okay, and this is an example of a unimolecular. My connection is unstable. I hope you can hear my audio. Okay, so we say that step 1 is the slow rate determining step because the rate equation suggests that a single N2O5 molecule is involved in the rate determining step. Okay, can you please copy this down quickly, because we have about 8 minutes left, right? This is an example of a unimolecular mechanism because there is only one species in the rate determining step. Okay, so please copy this down quickly, 1 minute, so that I can finish off example 8 before we finish this session. Okay, so that 1 minute is up. I will move on first. If you need to go back later on when we have time, then let me know. Okay, so this time in example 8, we have a reaction of 2 moles of nitrogen monoxide with 2 moles of hydrogen to form nitrogen gas and steam. Okay, the following equation, the following reaction has 3-step mechanisms, which is step 1, nitrogen monoxide reacting with nitrogen monoxide to form X. Your X is an intermediate here, obviously, because it does not appear in the overall equation. And then your X reacts further with hydrogen, okay, to form Y, right? And then your Y reacts further with hydrogen to form nitrogen and H2O. So that's where you get your final product is. Now the rate equation is given. Rate is equals to K times the concentration of nitrogen monoxide to the power of 2 times by the hydrogen. Okay, now my question is, which one, okay, which one of the 3 steps is the rate determining step? Step 1, 2, or 3? Can everyone try to answer me, please? What do you think? Step 1 or step 2 or step 3? Rate
One.
determining step, the slow step.
One.
One and two.
One.
I'm hearing
One.
1. I'm hearing 1 and 2, but the question is asking for just 1. Okay, only one of the 3 steps will be the slow step. The others would be fast.
One.
1.
Two.
Yes.
Someone is saying 2. Any more?
Okay. I think it's 2.
Someone thinks it's 2 now. Look at the rate equation to give you hints. Sorry? Any more? 1 and 2 so far. I'm hearing 1 and 2, 1 or 2. It cannot be 1 and 2 because it can only be one of the 3 steps.
Wait, no. I think it's
Yes.
2.
Is it 2?
Now I'm hearing more 2 than 1. Any more? No more. Okay, the answer is step 2. Okay, now why is it not step 1? Now, whilst nitrogen monoxide appears in the rate equation, step 1 does not show hydrogen. Okay, the rate tells us that both the nitrogen monoxide and hydrogen must be in the slow step. Right? Now, step 2, why is step 2 the rate determining step? There's only H2 and X. Now, if you look back, what is X? X is a combination of nitrogen monoxide and nitrogen monoxide. Okay, in the rate equation, it tells you that 2 nitrogen monoxide are involved in the rate determining step. So actually, if you think about X as being NO plus NO plus H2, step 2 is your rate determining step. Okay, are you happy with that?
Yes.
Okay, so step 2 is the rate determining step as hydrogen appears in the rate equation. X is a combination of 2 molecules of nitrogen monoxide, and combination of step 1 and step 2 agrees with the ratio that appears in the rate equation. So what do I mean by this? Step 1 shows you 2 molecules of nitrogen monoxide. That's why second order. Step 2, 1 molecule of hydrogen monoxide. That's why it's first order. Okay, can you please copy this down? You have about 2.5 minutes left. Okay, the one after this, I will just ask you to copy it first, but not on Zoom. I'll send you the slides and you copy it down on your notes so that in the next session, I can just go through it quickly and then move on.
Yes.
Yes?
Is it only always one no slow step?
Yes, but it's not necessarily the first step, but there's only one slow step and the rest will be fast. Okay?
Okay.
There cannot be two slow steps in a reaction, only one rate determining step. But so far, coincidentally, it's the first step, right? But not necessarily. It can be step number 2, step number 3, or 4 or 5. Okay, it all depends on the type of reaction. Okay, so just to let you know, I just started marking your assignment on Sunday, for Sunday. I may need you to send me, please send me the drawing of your graphs, because the working is not enough to check, it's not enough to check your working calculation. I need to look at the graph as well, right? So over time, if you know, I will ask you to send me the graph. But if I haven't asked you to do anything, that just means I haven't started marking your paper. Okay, right. We have less than a minute to go. Is there any questions or any problems so far?
Miss, for me, once I get printer ink, do I need to redraw the graph and send it to you?
No need to redraw it, but just I mean, no need to send it to me, but redraw it on your notes, on your paper. Okay.
Redraw.
Nabil,
Yes.
did you ask me something?
No.
Okay, right. I think the session will be ending soon. If